Hello, everyone. Can you hear me? Can you see the title slide?
Yes, we do. Thanks.
Okay, so I will address in my talk the handling of GNSS biases which are essential in particular for ambiguity resolution. I will also give an overview of the available IGS bias products. That's the outline of my talk. So in the first part, I will highlight the code biases. And here the applications are listed. They are required for double difference wide-line ambiguity resolution when using the pseudo-range methods, relying on the Melbourne-Webber linear combination in the clock analysis. When using the ionosphere-free linear combination, pseudo-range supported PPP, not for phase-based PPP, and of course also for ionosphere analysis where you use a different linear combination, the geometry-free linear combination. This slide gives an overview of the current GPS constellation. So the satellites are ordered according to the space vehicle number. Then you have the PRN number, the satellite generation, and the available code observation types. And it's really a wide variety of this kind of types. This listing may be not complete, but also very interesting is the difference between the generations. So you see here the older generations here just providing 3 observation types, and the latest block 3A generation really providing many types. Now, why do we have this kind of biases? So due to satellite and receiver hardware, pseudo-range measurements recorded in different tracking modes show systematic deviations. These biases cannot determined in the absolute sense. And also very important, there is a one-to-one dependency of these biases with clock parameters. And exactly for this reason, the following convention has been agreed upon concerning GPS clock corrections. So the ionosphere-free linear combination of C1W, C2W assumed to be unbiased or error-free. And so therefore other types of pseudo-range measurements are corrected accordingly, for example, as follows. So you have the C1C observation and you would like to make that consistent to C1W. So originally you added this C1W minus C1C DCB value, and nowadays CODE provides so-called observable specific signal bias values. So they are pseudo-absolute, and here is the formulation. And below you also have specific values as an example for a particular satellite. The important thing is that these values come from clock analysis, ionosphere analysis were combined. So you could also form C1W minus C1W, or you could also verify that the ionosphere-free linear combination of C1W and C2W would give this 0 conforming to the mentioned assumption. Here is a listing or an overview of the code bias products. Let me start with the ionosphere analysis community providing for decades interfrequency values. Here you see the link to the products they derive. Then we at CODE provide C1W, C1C reference values for making the data consistent for the GPS constellation. An important contribution comes from the IGS multi-GNSS extension, AMGEX, where 2 analysis groups provide differential code biases for all constellations. And finally, a kind of different product group is the code phase bias products accompanying the individual clock products generated by each individual analysis center, so in the product folder. Phase biases, they are required for single receiver ambiguity resolution performed in the PPP analysis mode. Let me directly start with an overview of the IGS phase bias provider. So here you see, so I took this information from the website, from the PPP working group, which has been established to address with this particular type of biases. And you see here the availability for 5 product lines, so rapid, final, AmChecks, Repro 3, and real time. Now, not all provide phase biases in Bias-SINEX, so some of them provide integer clock corrections or phase clock corrections, and provide the wide line phase biases in the clock header or in a separate file. But many of them already provide the phase bias information in the Bias-SINEX. And I guess it's worth to show you the way how to use this information. So the interested PPP AR user has to comply with the following rules. So he has to use consistent orbits, clocks in ClockRinex, and the biases. The bias file should contain bias data records for code and phase observations. And they have to be consistent with the associated ambiguity fixed clock products. And they have to be applied in following the equation here. So measurement equals to the computed measurement plus the bias, or alternatively, depending on the user's preference, measurement minus the satellite bias gives the computed value. And these OSB data records are generally labeled with a 3-figure identifier following the Rinex 3 standard. And following this convention, the user's PPP software should be finally able to recover the integer nature of the ambiguities for the wide lane when using the Melbourne-Webber linear combination, subsequently for the narrow lane ambiguities using the ionosphere-free linear combination. And satellites for which phase biases data is unavailable, they should be suspended for ambiguity resolution following the no phase bias, no ambiguity resolution rule. Basic rule we consider appropriate, because this also allows to the product providers to include systems where you do not have ambiguity resolution, for example, GLONASS, so that this kind of observations still contribute to a PPP solution. For more details, you have a link here at the end at the bottom of this slide. This is an example for GPS 2-frequency case for a particular satellite. So in the ideal case, you have the bias values for all involved or all available code observable types indicated here in blue. Also then the situation for Galileo, and in the red, the phase biases for the various phase observable types. And you see for the same frequency, the phase biases are identical. So we assume here that the phase measurements on a specific frequency are aligned with respect to each other. So again, important is that we do ambiguity fixing for between satellite ambiguities. And so you get then positions with respect to the entire receiver network of the IGS in a specific geodetic datum, currently ITRF 2014. And obviously this method is competitive to double difference ambiguity fixed analysis. So in particular for people doing POD analysis for LEOs, this is the method to use. Additional remarks. So one thing is concerning the PCO antenna corrections for the Melbourne-Wuppertal linear combination. So we know that for the latest generation of GPS satellites, we have a significant satellite antenna offset between L1 and L2, and also for Galileo. And currently, two conventions are used for the application of PC phase center corrections to the Melbourne-Wuppertal linear combination. So either you do not apply any correction, or you do apply that. And therefore, it was decided really to find here a common way to model that, and it's reasonable really to apply the corrections. And there is planned to change for those which follow still the old convention to really apply the phase center correction also for the Melbourne-Wuppertal linear combination, because this has a direct impact for the wide lane biases. For more information, please be referred to the specific IGS mail I specified here. Another remark is concerning DCB information. So CODE does make the available this information also in other formats that are now no longer up to date. For example, the Bernie's DCB and in particular also the very old CC to non-CC P1C1 files. And we would like to announce here in advance that we will continue discontinue this service as of the transition to the ITRF 2020, which is expected in mid this year. And one reason to do that is really that we noticed that some of the IGS ACs still use the old files where you do not have a space vehicle number, where you do not have the time window. And here is an example. So the most recent constellation change caused some issues in the combination of the IGS results. Let me summarize the results. So CODE biases are essential for wide line ambiguity resolution, namely for double difference and for the zero difference case. We are clearly moving from a differential to a pseudo-absolute or an OSB representation, which shows its advantages regarding multi-GNSS. Phase biases, along with CODE biases, enable single receiver ambiguity resolution, or briefly PPP AR, and the provision of such biases in OSB form conforming to the Bias-SINEX seems to be becoming more and more established within the IGS. The Bias-SINEX data format is approved by the IGS and already widely used also for this PPP AR application. And we heard already several times how consistency is the key for success. And this is all I have for today's presentation.
Thank you, Stefan. Are there any questions? I don't see something in the chat. There is one coming up from Christian Felici. Please.
Yes, it's a very basic question. Sorry about that. I haven't seen these acronyms before, so I would like to know the meaning. If you have a link in the internet where we can read more about them.
The answer is pretty simple. So this acronyms we will find in the RINEX 3 and the RINEX 4 format description. You have a summarized folder at the IGS web page. You'll find all these documents. But please send me a mail, and I could also send you the direct link to this file. Here we have it already in the chat for the RINEX 4.
Arrived in the chat. Are there other questions? Okay, if this is not the case, then we can switch to the last presentation. Thank you, Stefan. Johannes now will report on the troposphere modeling.